Okay, so last time where we left off, let me do a quick, brief review of what we discussed. We were talking about the wave properties of light. So let me go back to slide number 2 first. And this shows the schematic of the electromagnetic wave propagating through. Now, if we take a snapshot, this is a traveling wave traveling at the speed of light, 3 times 10 to the 8th meters per second. And if I take a snapshot in time, then I measure this wavelength, which is 1 full cycle, which is what we call the wavelength of light. If, on the other hand, I sit at a point on the x-axis and I watch the waves passing through me or through my detector, and I measure how many times the wave goes up and down per second, that's what we mean by the frequency. Okay? So frequency is how many times per second does the wave go up and down at a point in space. Right? And of course, the wavelength is taking a snapshot at a fixed time and measuring the distance along the x-axis of the complete sine wave. Okay? So I'm just doing a brief review here. Do you have a question? No? Okay. So we understand wavelength and frequency. Now, for light, which we'll be talking about a lot, the wavelengths of light that we'll be talking about in the visible region are 400 to 700 nanometers. Right? This is the region of lambda that we are interested in. And the frequencies are of the order of 10 to the 15 hertz. Okay? To say that one complete cycle of the sine wave passing a given point in space will take only about a femtosecond. That's 10 to the minus 15 seconds. So remember, the period is 1 divided by the frequency, or 1 over tau is the period of the wave. That's how long it takes for the wave to go from a maximum to a minimum back to a maximum again. Sitting at a point, watching the waves cross you this way. So the red line, the red curve, for example, will go, you'll see the minimum, and then you'll see the maximum, and then you'll see the minimum again. So one complete cycle of the wave is what we call a period. Okay? Okay, I thought I just wanted to clarify that. Now, the other point that we discussed last time is that according to Maxwell's equations, intensity, which is, we said was measured in watts per meter squared, that's the light intensity hitting the surface. Right? So in other words, or it's the energy, I guess you'd say. It's the rate of energy hitting a surface of material is what we call the intensity. Visually, that's what we call brightness. Right? That's the visual concept of brightness is quantified in Maxwell's equations. That intensity can be specified in, how many joules per second per square meter. How many joules per second per square meter are hitting a surface, and that is what we mean by how bright or how intense something is. It turns out that intensity is proportional to the square of the amplitude of the electric field. Okay? In other words, the amplitude of the electric field is, in the previous slide, this one, is the distance, the maximum strength of the electric field within the sine wave. This is the amplitude. Right? The higher the amplitude of this wave, the more intense is the light, and the brighter it appears to our eye. Okay? But the crucial point is that, and we're not going to drive that here, is that intensity is proportional to the square of that quantity, what we call the square of the amplitude. Okay? And we're going to use that feature a lot in our derivations. And furthermore, the light intensity on the screen is determined by the sum of all the electric field vectors from all light sources added together at a point. So if I have multiple light sources, they each contribute the electric field. I add those electric fields together if they're in phase, and I get a new electric field that's higher, and that will make the light more intense. Okay? So we have to calculate, if there's multiple sources, then we calculate what we call the resultant electric field vector, or the net. And we said last time we can disregard in our calculations, we won't use the B field in future calculations, since both B and E are in phase with each other in a sine wave, and they contribute equally to the light intensity. So for abbreviation purposes, we're only going to talk about the electric field, because that really is what can be used to describe, relate to intensity. We've already included the magnetic component in this equation, because the electric field component contributes exactly the same as the magnetic field component of the sine wave. So that's step one. Okay. Now, how can we actually observe? Remember, there are two phenomena that we are primarily interested in. One of them is interference. What happens when two waves from two different sources arrive together at the same point in space, and that's called interference, which we want to study. And the other is diffraction, which is the fact that as light goes through a slit or a hole in an opaque screen, then it not just forms a shadow going straight through the hole or the slit, but it actually deflects outward and it expands. And that bending of light through the hole is what we call diffraction. Okay, so we're going to talk about these things together in the example. And the first example in the book is what is called the Young's double slit experiment, and named after the famous physicist that first discovered this phenomena. And basically, the idea is that if light is a wave, then interference effects should be seen where one part of the wave, say the wave that goes through a slit number one, can interfere with another part of the wave, for example, light that goes through slit number two. And one way to study this interference and diffraction is to study what happens in a double slit experiment. So if we were to do this experiment with our normal light patterns that we get in the room, and we put a bright bulb upstream to provide a light source. In this case, it's described as sun rays going through the screen. Then you might expect that we simply get two bright lines here, which is the shadow of the opaque screen where the light is able to pass through, and you just see basically the shadow effect of the two slits right here. In the experiment that Young did, he was able not to show that what you actually observe is a bright spot in the middle with lower intensity bands, or what we call fringes, on the side that eventually taper out to zero on either side. And there are a couple conditions that have to be satisfied. Number one, the spacing, the opening of these slits, and the spacing between the slits cannot be too much greater than the wavelength of light. So typically, for example, when we do these problems, the spacing between the slits is no more than 0.5 millimeter, and the width of these slits might be, for example, 1/10 of a millimeter. That's still a lot more than the wavelength of light, but it's not exorbitantly large. Right? Secondly, it's most easily observed when we have monochromatic light, which means that there's only light of one wavelength or frequency going through. It's most easily observed. Lasers are a really nice way of doing that. A blue laser, a green laser, a red laser. Any of those will suffice to make a nice, and you'll see that in an example in the next slide. So understanding how this intensity pattern develops is what we're focused on, and you'll have homework problems that will deal with that as well. And you can start looking at those as you read through the book this week. Okay. What do we have? How do we describe this theoretically? What's the concept or the picture that we have? Well, we talked about the blue lines being the area of the region of the wave where there is a crest. So we said that when a plane wave is propagated through space, in this case starting from the left going to the right, that we can describe what we call a plane wave as one in which the crests of the wave form lines that are perpendicular to the direction of motion. So the light is traveling through the slit, but we can think of these sine waves that are propagating and passing through the slit. So these blue lines are lines that are actually moving at the speed of light. And some of that light is going to propagate through the hole. As it goes through the hole, then Huygens' principle says that the light will spread out equally radially in all directions from any point on the wavefront. And so we generate these new wave crests, which are spherical surfaces or cylindrical surfaces, if these are slits. And this whole thing is a dynamic picture, namely that these blue lines are moving from left to right. And eventually what happens is they hit the screen. So if light is acting as a wave, there should be an interference pattern like the one we saw with the water experiment on the previous slide, which is over here somewhere, slide number 6 that we talked about. And keeping in mind that these are moving waves, so we have to take the time average of what we call the resultant of the square of the amplitude of the resultant electric field. So by resultant electric field means we're going to add the electric field contribution. If we go to a point here on the screen, we are going to add the electric field component due to light coming through S1 to the electric field component that is coming through S2. And you'll see that more clearly in a couple slides as we move. Any questions so far on this? Everybody get the idea? The blue line is the crest of the wave. And therefore, the wavelength is the distance between these two blue lines. Notice that that does not change even as it goes through the slit. The spacing between those lines are the same before and after because the wavelength has not changed. Now, an actual photograph of this done with a double slit experiment done with double slit apparatus shows that on the distance screen, that if this is exactly midway between the two slits, so in this case, you want to visualize the light coming towards the projector, and the opaque screen has two vertical slits, two vertical slits that the light is passing through, and the reference is that at the center of that photograph is the midpoint between those two slits. Okay? So the midpoint between those two slits is what you are seeing at where this orange arrow is indicating. And if I were to draw a line across here, measuring how does the intensity change as a function of distance across the horizontal direction, I would get a profile, a line intensity profile that goes up and down like this. So one of the points that we want to understand is how does how do we explain this pattern? How do we explain the peaks that occur, and of course the minima that occur, and ultimately how do we describe or explain the entire intensity pattern based on the wave picture of light? Right? So that's the goal. We want to find out how do we derive or explain this intensity pattern from the double slit experiment. Now, in some of the slides I'm going to show you, you'll see that while in this particular example the peaks decrease in intensity as you move away from the center, in some of the future slides you'll see the peaks do not fall off like this. And that's going to be because of a reason we'll explain later. For right now, we want to basically focus on where are the peaks and where are the minimas in distance from the center of the screen. And so that's sort of the gist of what we're shooting for. Okay? So this is a slide with a theoretical picture of how we're going to explain this. How are we going to explain the fact that the intensity varies from a maximum in the middle, it goes through up and down, high and low areas. We call those bright areas fringes, by the way, so in the future we'll refer to those lines or stripes as fringes. But we want to know how that occurs. And so the basic description is going to be that this interference is going to explain this intensity variation, and it occurs because at each point on the screen is not the same distance from both slits. So for example, if I were to pick a point that is exactly at the middle of the screen, which is a projection of the distance from the midpoint between the two slits to a distant screen, at that point you can see that light travels the same distance whether it goes through slit 1 or slit 2. Therefore, since the phase, you notice you see the phase is where exactly the peak or the minimum, the max or minimum is, since the phase is the same as they arrive at the slit, then the phase will be the same when they reach this point because they both traveled the same distance and they're traveling at the same speed. So by the time they get here, you'll see that what happens is the crest of the wave from S1 will match the crest of the wave from S2, so the amplitude of the resultant wave is double. So I try to draw a picture of that. So the basic idea is that if this is a wave which is coming from the first slit, which we will call E1, and this is a function of, the way it's drawn there, it's a function of distance, which is we'll call x, and I'm adding to that a wave of the same amplitude and of same phase, then the sum of these two waves will be the same sine wave, but basically with twice the amplitude. So the sum, so this is E2, as a function of distance, x in this case is the distance from the slit to the screen, and if I add these two together, then the sum will be one that goes up like this, double like this, right? So this will be the wave that is arriving at the point in the center of the screen, and we said that the intensity, and we'll just put in a proportionality constant here, is equal to some constant k times the square of the resultant amplitude. And I'm going to call the resultant amplitude E theta 0. Okay? And by that, what I mean is by E theta, if E is a function of theta, it's E1 plus E2. Okay? And this, when I add these two together, then this will be, this one is, if I write this one is sine of, let's write out the whole thing, kx minus omega t times E1 plus E2, which is also a sine function of the same wavelength and the same frequency. And when I add these together, I will get a new amplitude, E theta 0, which is, or I'll call this E theta. So this is E theta is equal to E theta 0 times a sine wave of the same frequency and wavelength. Right? So when I add them together, then I will get a another wave, which in this particular case, in cases that we will consider, the amplitude of the wave in the going through the first slit will be, in most cases that we talk about, will be the same as the amplitude of the wave going through the second slit. So this is for slit number 1. And E2 is the electric field going through slit number 2. Okay? And in the case that we just described, then the case for the combined amplitude of the electric field is 2E0. We can drop the subscript and just call this E0. So this is 2E0 times sine of kx minus omega t. So what happens? I add the two sine waves together and I double the amplitude. Right? Each one of these has amplitude E0. This one has amplitude E0. This has amplitude E0. So this one has amplitude 2 times E0. Okay? That's when you add two sine waves that are together that are in phase with each other. Now, notice that if I added them, if I added a displacement distance of half a wavelength to this one, then what I would have is I would have a case where E2 is out of phase with E1. So in that case, in this case, they are, we say these are in phase. Okay. And in the case of them being out of phase, then E2 will be exactly the opposite. It will go negative when E1 goes positive, and it will go positive when E1 goes negative. And consequently, I can't draw it because I'm running out of room here, but now E1 plus this E2 gives me a resultant field, E theta 0, which is the resultant, is equal to 0 everywhere. Okay? Everywhere. So the cancellation is complete. I get 0 intensity on the screen, and there's a dark spot. Right? So this is the two sine waves arriving in phase. These two are the two sine waves arriving out of phase with each other. And I get two completely different amplitudes when I do that. Right? In one case, I've doubled the amplitude. In the other case, I've reduced it to 0. Okay? That's basically addition or adding of sine waves. Any questions on that so far? Okay, so now we can return to the initial. If anyone sees my pointer, let me know. Oh, there it is. So now we can return to our initial our case study here with the light coming from the two different slits. So in this one, I'm clearly going to have a bright spot because I've doubled the amplitude of the electric field, and the screen gives a big bright spot. Similarly, supposing that I pick a point, now let me go back and reduce the lighting again so that you can get a better view of the PowerPoint. Supposing I now consider a distant point P where the path difference between the light coming from the upper slit and the light coming from the lower slit is equal to this distance, this little segment here. So I draw a perpendicular line from the midpoint of the slit down to the second ray, which is the light from at S2 that is propagating to a distant point P. And let's suppose that that path difference is exactly equal to one wavelength. So this, the light from this slit has traveled one extra wavelength of distance compared to light from the upper slit. Right? That's equivalent to displacing one of the sine waves by exactly one wavelength. So if I, let me turn the lights back on again. So if I displace this E2, which is the light from the second slit, by exactly one wavelength over, then they would still line up. The maximum from the electric field in E1 would occur at the same time as the maximum of the electric field in E2, because I've moved this whole distance over exactly one wavelength. And so if I do that, then I still have an additive feature of the electric fields, and I've doubled the electric field amplitude when I add them together. And so I will again get a bright spot on the screen. I've doubled the amplitude. If I were to move this by 2 wavelengths over, this whole sine waves, it now gets moved 2 wavelengths over, then the maximums will still line up, and we will still get a constructive interference or a maximum intensity. So by doing this, if I move this over an integral number of wavelengths, then I have, or if I should say, if one of the rays travels an integer number of wavelengths further than the other one, then the 2 waves will still arrive in phase together, because they will have traveled either 1 wavelength longer than the other one, 2 wavelengths farther than the other one, or 3 wavelengths further than the other one. Okay? So that's a general condition for getting an intensity maximum. And the way we describe that is that path, whenever that path difference is equal to, which is, by the way, on this screen, this path difference is this short segment right here that I'm pointing to between the opening of the slit and the projection of the line from the first slit down to the path of the second slit. This short distance right here turns out to be equal to d sine theta. So d is the distance between the slits. So d is equal to the distance between the slits. Theta is equal to the angle from the slits to the screen, to the point P, to the point on the screen. And so the path difference between rays of light traveling from the upper slit to the distant point minus the path difference from the lower slit to distant points must be equal, when that is equal to lambda or 2 lambda or 3 lambda, etc., then I will get maximum constructive interference. Maximum constructive, or another way of saying it, a bright spot. Okay. Maximum constructive interference. Okay? And this path difference, as we can see in the slide up there, is just equal to d sine theta. Okay. So the condition for a bright spot or maximum constructive interference is that d times sine theta is equal to any multiple integral multiples of the wavelength of the light that's going through it. And when that happens, the 2 waves will arrive in phase together. Okay? It's a condition for, so every time I see it, so now I have a way to predict where these peaks occur in the diffraction pattern. So going back now to the previous slide, I now know something about how to predict where these maxima occur. This occurs when d sine theta equals, at a point on the screen where d sine theta equals lambda. This occurs where d sine theta equals 2 lambda. This one occurs where d sine theta equals 3 lambda, etc. So those conditions, that condition then defines the condition of finding a bright spot on the screen. All right, any question on that? Okay, all right, well, let's see. Okay, now what about the dark spot? Well, the dark spots on the screen are going to occur when I have complete destructive interference. So in that case, I have a sine wave where the maximum of 1 occurs from light from the one slit occurs at exactly the same time and location as the minimum electric field from the other slit. Okay? And that's going to occur when the path difference, so in that case, for destructive interference, the path difference must be equal to 1/2 lambda, 3/2 lambda, 5/2 lambda, or etc. Right? It's basically a half integer. We usually write this as m plus 1/2 times lambda. So we're going to get destructive interference. Destructive interference when d sine theta is equal to m plus 1/2 times lambda. Okay? So this is now the condition will tell me where on the screen, what angle on the screen that I will, the angle from the normal that I will observe where the dark spot of the pattern occurs. And we'll have an example here where we'll actually go through that and describe it. But so these two conditions then are the ones that we have now derived for the conditions. And again, we're defining theta in the orientation that you see in the screen here. So theta is the angle between the normal to the double slit screen, halfway between the two slits, up to theta is this point looking at a distant point P, which is, of course, depending on theta, is a point, any given point on the distant screen over here. Okay? And consequently, because we do these geometries in space, we actually measure where these minimums occur or maximums occur at given distances y, from the center, we'll call this the center of the screen, then we can use the trig relationship that this angle theta that we're talking about has the property that if I'm a distance L away from the double slit, then this distance y is just equal to L times the tangent of theta. So if I measure the maxima at different points along the screen or different values of y, I can calculate what theta is for that, right? And if I can calculate what theta is, then I know one of the parameters in this equation. I know what sine theta is, right? Now it turns out, and we'll see this in a couple examples, that when you're looking at regions where theta is small, and small is sort of in the eyes of the beholder, but let's say when theta is less than 20 degrees, for example, then we can use a small angle approximation if that, by the way, only if we measure this in radians, of course. 20 degrees is what we're used to, 0.3, let's say 0.35 radians. That might be another way of putting it, okay? Because we need numbers in radians. then we can use the small angle approximation that sine theta equals tangent theta equals theta, right? Approximate, right? So this is called the small angle approximation. And this turns out to be pretty useful to do some of these problems. Now, it's not always true that the results are curved for small angles, but when they do, it simplifies the math because when I calculate tangent theta, I just put that in for sine theta, right? And so I can use that. I've got one of the variables to calculate something in my equation. Now, typically what one can do with this is use this equation is to measure the wavelength of light. So for example, if I have a screen where, and we'll see this example here in coming up in the next, probably next problem, if the distance between the slits D is 0.5 millimeters, right, and I measure Y, then I can find lambda. Right? So I can use this relation to actually, and this apparatus, to measure the wavelength of light, which we will do in the next slide. Okay? Questions? You can feel free to raise your hands. I'm trying to go kind of fast to get through this, but you feel free to slow me down. Yeah.
So why would you have the overall reduction of light intensity? So you'd obviously have a pattern of where you have the destructive interference, but wouldn't it be constant until it basically ends?
Yes, yes. So the answer is yes, and that is probably going to come later. But basically, you'll see in a couple examples, sometimes these peaks do decrease with distance away from the screen, and sometimes, as you will see in a couple others, they do not. And we'll get to why the difference is. But for right now, that's kind of it's a higher level point. It's an important one, but I'm afraid if I try to explain it, we'll get ahead of ourselves. Yeah, but good question. Okay, so simply put, these are the equations that we just derived. The occurrence of where to find the maxima occurs when d sine theta is equal to an integer m times lambda, where m is equal to 0, 1, 2, etc. And d sine theta, when it's equal to m plus a half times lambda, then we get destructive interference because I've now, instead of displacing the second wave by an entire wavelength, I've only displaced it by half a wavelength. And when I do that, then the maximum of one wave lines up with the minimum of the other. And so that's the way we get this condition for destructive interference. Now, there's a, well, let's review this and come to maybe a little bit different conclusion, a new conclusion. So if the phase difference between the two waves are, we said that if the path difference was 0, or it was lambda, or it was 2 lambda, then they add in phase. But if we look at it in terms of phase difference, what we're really saying is that when the phase difference between the two waves is 0 radians or 0 degrees, or the path, the phase difference between the two waves is 360 degrees or 2 pi, then that means exactly the same thing as shifting the sine wave by one wavelength relative to the other. Then I get maximum brightness, and that will occur when the two waves are added together. Similarly, if the phase difference between the two waves is 180 degrees or 540 degrees or whatever this number is in degrees, 5 pi radians, etc., then the two waves will add out of phase, and I get minimum brightness or a dark spot. And this occurs when the path difference is 1/2 of a wavelength, 3/2 of a wavelength, or 5/2 of a wavelength. So we see that there's a correlation between path difference and phase difference between two waves. And the relation is, and this will come over and over again in the problem, is that if I have a path difference L between two waves when added together, the one travels a distance L further than the other, there will be a phase difference between those two waves, which is equal to L times 2 pi divided by lambda. So every advancement of wavelength L, or extra path length of wavelength, every additional path length, distance of lambda will increase the phase difference by 2 pi. Or in general, any path difference that if the one of the rays travels any distance L, which in our case happens to be d sine theta here, this d sine theta is actually the path difference that we're talking about, times 2 pi over lambda gives you the phase difference between the two. Okay? So that's an important principle. Phase difference is equal to path difference times 2 pi over lambda. I will probably repeat that every class for a while. The phase difference between two waves when added together is equal to the path difference between those two waves. What was the difference in path length that they went? Times 2 pi over lambda. Okay? So we just went through that in a simple case here. When one wave goes exactly one wavelength, travels one wavelength further than the other before it recombines, then it will have advanced and a phase difference of exactly 2 pi, which is of course what you need to get constructive interference. Okay. Any questions? Right. I mean, a lot of this does take studying on your own. This is really an additional supplement to your own reading and studying. So a lot of these things, we can spend a lot more time going through it to make it clearer, but if we do that, then we don't get through our material fast enough. And so if you spend some time, if you spend your time looking at the problems and the book, then hopefully the combination of these two will make it clearer. But these are hard concepts, I mean, they just take time to sink in. You have to think about this in a quiet room with no headsets on. Or if you're going to use headsets, use the noise canceling headset. Okay? So 2 pi over lambda is the conversion factor from path difference to phase difference. Learn this, okay? That's just because I think it'll help on some of the problems. Okay, so now we'll do an actual example. We have a double slit experiment that we want to analyze for the locations of the maxima and the minimum. And so we're going to look at a particular, let's suppose we have a double slit experiment now. We want to calculate the distance between the intensity maxima on a distance screen. So this particular example is one where we're given some information. There are the slit distances, the slit spacing. So the spacing between the slits is half of, 0.1 millimeter. So we've got a 1/10 of a millimeter spacing, so D is equal to 0.1 millimeter. I have a wavelength of light that is incident upon the double slit, and I'm asked a question to calculate something about the intensity. I know that the wavelength of the light that's hitting the slit is a certain amount, which we will call, in this case, is 500 nanometers. Okay. And it's a distance L to the screen, and our screen distance L is given for our measurement screen is 1.2 meters. And we want to find out, there's a question here, what is approximately how far apart will the adjacent bright fringes be on the screen? In particular, let's calculate the distance between the second bright fringe and the first bright fringe. So, by the way, when we talk about these, the central maxima is called the central fringe. The first one over off there is the first fringe. This X1 is a location of the first fringe, X2 is a location of the second fringe, etc., etc. So how far apart will these two peaks be on a distant screen? Well, let's see. So what do we know about X1, X2? Well, we know that X1, any distance X1, is related to the angle theta, for which that maximum occurs, and we get that X1 is equal to L times tangent theta 1, right? And X2 is equal to L times tangent of theta 2. Okay? So there are, and these are the correspond to the first and second maxima that you see up there on the screen. So we can apply now the condition for the first maxima right here is going to occur when the following condition is met, that d times sine theta 1 is equal to lambda. And the second maxima is going to occur when d sine theta 2, which is the path difference, right, between the upper and lower path, the upper and lower ray, is equal to 2 times lambda. Right? So I know what L is, and if I want to calculate x2 minus x1, I need to know what theta is, right? Fortunately, I can get theta because these two conditions tell me exactly how to calculate that, and since I know both the wavelength and the spacing between the slits, I can calculate that sine theta 1. Put this somewhere. Sine theta 1 is equal to 500 microns. 500 nanometers. I'm talking about. Is equal to 500 nanometers divided by the distance between the slit, which is 0.1 millimeters, and this turns out to be 0.005, right? Sine theta is equal to 0.005, and obviously because this is a small angle approximation, I'm going to find out, or actually just because I'm going to double the value in the numerator here, I can say that sine theta 2 is equal to 0.01. Okay? So clearly we can use the small angle approximation because sine theta is much, much less than 1. And so I can just take the, that sine theta is equal to tangent theta. So x2 minus x1 is equal to L times tangent theta 2 minus tangent theta 1, which is sine theta 2 minus sine theta 1. So this becomes equal to 1.2 or 1200 millimeters, if it's in millimeters, times 0.01 minus 0.005. And that number turns out to be 6 millimeters. So the distance between the first two maxima of the fringes, the bright points, parts on the distant screen, is in this case is 6 millimeters. So we've answered the above question. We've done our first application of the condition for intensity maxima and for intensity maxima, applied it to the geometry of the screen location relative to the angle and the distance from the slits, and answered the first question. Right? So it's the first application of using these equations to get a result. Now, we can ask the question, will there be an infinite number of points where constructive and destructive interference occurs, or are there only a finite number of points? In other words, the way I've drawn this here, or the author has drawn this here, the spacing is equal, the plane goes out to infinity. Might be reasonable to suppose that there's an infinite number of maxima and minima on the screen. Right? Is that in fact true? Is it infinite or finite? And the second question, well, let's answer that question first. So, what we can do is what we can do is let's write out the equation. Where do the maxima occur according to the equation? The maxima intensity occur when d sine theta is equal to m lambda, and m equals 1, 2, 3, etc. And does m go out to infinity, or is it finite? Well, if I solve this for sine theta, then I get that sine theta is equal to m times lambda over d. And lambda over d is a constant, right? M can increase, but there's another condition, is that for any real solution for theta, sine theta has to be less than or equal to 1. Right? Eventually, m is going to get so large that sine theta in this equation could get larger than 1, and there is no solution. So the maximum value, so the maximum fringe number, or the maximum, I'll call it the maximum fringe number, m is equal to d over lambda modulo 1. I guess I'm trying to remember how you do this in terms of fractions, but there's a maximum m such that m is, how do I say it? There's a maximum fringe number m such that m times lambda over d is still less than or equal to 1. In fact, equal to 1 would be exactly 90 degrees, which would be at the infinite edge of the screen, and we only measure finite distances, so we'll put it this way. And now, there is a maximum integer m to satisfy this equation, or there's a maximum integer m to satisfy that m must be less than d over lambda. So it is finite. There are only a finite number. What that means is that the spacing between these maxima starts to get larger and larger because there's only a finite number as you go out to 90 degrees, which is the point x equal to infinity on the screen. So it is limited. It is limited, and it is limited by this amount. Now, if I were to ask what is the total number of fringes, then what I would do is I would first calculate this. We will call this m max, so let's call this the maximum m. So this leads to some m max, right? And the total number of fringes is going to be 2 times m max plus 1. Right? Why 2? Well, because there are just as many fringes above center line as there are below center line. So that's a factor of 2. So whatever large m max is, which is the maximum number of m, there's going to be that many on this other side of the center line. Right? So that gives 2m. And then you have the central fringe itself, which adds another one, which is 1. So total number of fringe would be 2 times m max plus 1. And you get m max by the maximum integer that is that satisfies that equation. Okay? So the answer is, let's go to the next question. Are there an infinite number or a finite number of maxima on the screen? There is a finite number. Are neighboring points of constructive interference uniformly spaced, or is the spacing between neighboring points non-uniform? Well, that's connected to the first question. We just went through that. If there are only a finite number of maxima, and I count them as I measure x out to infinity, then clearly the spacing between them is increasing. Right? Yeah, spacing is increasing, and it's finite. So that's just to kind of get you started on understanding how these, maximum and minimum work. All right? Any questions so far? Yes?
You said that they're increasing. Did you mean the space between each fringe or?
Each successive fringe, between adjacent fringes,
So
is increasing. So in other words,
is the first fringe farther from the center than the second fringe is from the first fringe? You know what I'm saying?
yeah. So because we're doing with very small angle approximations, the case we did here, they actually turn out to be very close to equal. So they are equal, but what I would say is that x3 minus x2 is more larger than x2 minus x1. That's what I'm saying. It's gradually increasing in the distance.
So x1 won't equal x2.
No, x1 is not exactly equal to 2 times
Yeah.
x1. Right. Yeah, not exactly. Right. And it becomes more obvious as you go to large angles. Okay, good question. Yes?
This may or may not matter, but when calculating the max fringe number, would it be n is less than or equal to d over lambda?
Well, yeah, but the equal sign occurs for 90 degrees. Remember, when you have equal sign, that's theta equals 90. Theta equals 90 is an infinite distance on the screen.
Oh, okay, yeah.
Yeah. So it has to be less than.
Yeah.
Okay, good question. All good questions. Any other questions? Okay. If you think of one later, still raise your hand. We can keep going. Yeah, here's an example where instead of calculating the spacing between the fringes, we can use the location of the fringes to calculate the wavelength using the same equation. We sort of hinted at that already. If I take the condition, this condition for maximum intensity, this one right here, then you can see that if I were to measure the values of theta where the maxima occur, and I know what d is, I can solve for lambda. Right? And that's in fact what we do, and there are practical applications where this is a useful device method for measuring wavelengths. Okay, so here's the example. The example is we have in this case, a spectrum of wavelengths that go through the two slits. The slits now are 0.5 millimeters apart, and they arrive on a screen. The pattern that you see here arrives on the screen 2.5 meters away. So let's modify our diagram and look at what we get here for this particular. So now we're looking at a case where L is equal to 2.5 meters, right? And I'm going to use a case where D is equal to 0.5. D is equal to 0.5 millimeters, right? And I'm going to, in this case, know what the value of x1 is, and it's for blue light. So you notice that as you go through the double slit, you begin to see maxima for the short wavelengths at the closest to the center. Then you see longer wavelengths, which is green, yellow, and red be the longest wavelengths as you move away. So it acts sort of like a prism, that it takes white light and it spreads it into the colors, and the colors of the light are located at different angles coming from the double slit, opening up this way, right? So in the way I've drawn it here, this distance, so we get a blue maxima. So here we have the blue maxima, and it occurs at a distance of 2 millimeters from the center of the slit. Right? So now what I can do is let's calculate theta. So, because we're obviously going to use d sine theta, I already know what d is. All I need to know is calculate theta, right? So tangent theta is equal to 2 millimeters divided by 2,500 millimeters. And I'm going to put that down on my notes here. So you get right out. Wrong note. And what I get for this is that theta is equal to 8 times 10 to the minus 4. So let's just say 0.0008. And therefore, lambda is equal to, this is the first order fringe, right? First order means this is the first time I see blue as I move away. Now, these are exactly first order fringes. If I had a broader screen, then I would see the pattern repeat. This is the m equals 1 case for those 4 colors. I would then, at a higher angle, find the m equals 2 for blue, green, yellow, red, and then they would repeat. So I get blue, green, yellow, red, blue, green, yellow, red, blue, green, yellow, red. This is m equals 1. The next one is m equals 2. The third one is m equals 3. So these are what we call the first order fringes because they're closest to the center, where I get a maximum. The maxima closest to the center are the lowest order fringes. Right? Because the first fringe is closest to the center. The second fringe is the second one over from the center for that wavelength. Right? So this is the first order blue, this is the first order green, the first order yellow, first order red. Right? First fringe for the blue, first fringe for the green, first fringe for the yellow, first fringe for the red. And then at n equals 2, which occurs at a larger angle, I'll repeat that again. Right? Why does blue come before red? Well, lambda is equal to d times sine theta, right? And for the maxima, and this is the condition of maxima. So the smaller wavelengths will occur for smaller angles. So I'm going to see the maxima for blue before I see the maxima for red. Right? So they're in the correct order, the way we think. They should go blue, green in order of wavelength. First I see the intensity maxima for the shortest wavelength, then I see it for the next shortest wavelength. And it says, right now I want to calculate what is the wavelength for the blue light. So for the blue light, it's going to be this times d times sine theta. Okay. I've just calculated tangent theta. This is clearly a small angle approximation. Therefore, it's equal to sine theta, approximately, and to a good approximation. So this becomes 0.5 times 0.008. 0.008. And this is in millimeters. So this is equal to 400 nanometers if I multiply it by 10 to the 6th. And I've now used this to calculate the wavelength of blue light. Okay. Isn't it simple? Looks simple now, doesn't it? D sine theta equals lambda, or m lambda. You'll get more challenging ones, or you'll get some similar ones, but you'll get practice with the homework. That's a good idea of doing that. Okay? So that's the problem. So you can actually use this to measure the wavelength of light. Okay? We good? Going once, going twice, gone. So, okay. Now Well, first of all, we have now defined and understood, although we did the particular example, but let me go back to the equations again. The conditions or the locations of how to find where the maxima and minima are given by those two, right? That tells me the angle where there's zero intensity, and it tells me the angle at which there's a maximum intensity for every wavelength of light that's hitting the screen. All right, now what I want to know is, what is the wavelength at some distance that is neither at a maximum or at a minimum? What is the intensity between the maximum and the minimum? How does it fall off from a high value to zero? Is it a cosine function? Is it a linear function? Is it quadratic, cubic? And furthermore, the reason it's important is because if light does act like a wave, then we should be able to use the wave properties to predict and get the experimental results that should be in agreement with these properties of the wave. So it's a confirmation that waves do in fact add together, they interfere, and we can calculate how that works. Okay, so how do we begin to do that? So we want to know, what are the intensities between the max and minimum? Well, to do this, we have to do a little more, add a little more theoretical work to adding these two sine waves. So up till now, we've only added sine waves when they are, when one has traveled a distance lambda or half lambda further than the other one. In general, that's condition is not necessarily true, particularly if I'm between maximum and minimum. So now what we want to do is find out how can I calculate the intensity as a function of angle, not just where the maximum and minimum, right? So the path to getting there is going to be the following. What we're going to do is say that the intensity as a function of theta is equal to some constant, which we'll call C, times the square of the electric field amplitude, E theta 0 squared, when we add two waves together that differ by, or that are out of phase by a given amount. So we label these in this notation up here as E10. So we're going to look at E10 times sine of omega t. Now you might say, well, what happened to the kx part? Well, I'll get to that in a second. And then we have the second part, the second wave, part of the wave is E20 times sine of omega t plus delta. So delta is the phase difference. So delta is equal to the phase difference of the two waves arriving at P, point P, on the distant screen. Right? That's what we're going to call that. That's what we're going to call delta. It's the phase difference of the two waves arriving at P on the distant screen. That's the only thing that we're really concerned about. And of course, the time dependence is because the wave, you're at a given point, and you see the sine wave going up and down the time, because you're resting at one fixed point. But there's a phase difference. What do we know about the phase difference? We know that the phase difference is equal to the path difference, which, by the way, is d sine theta, so let's just put that in there, is equal to the path difference, d sine theta, times 2 pi divided by lambda. Right? That's what delta is. And that's what defines what the intensity is going to be. Because now what I need to know is, when I add these two sine waves together, I'm going to get a new sine wave, which is going to have the same frequency and the same wavelength, but it's going to have a different amplitude. I'm going to call that E theta 0, and it's going to be sine of omega t plus some other phase. We'll just call it, q. It doesn't matter. It doesn't matter. The point is that I get a new amplitude. Once I know that new amplitude, then I can square it and calculate the intensity. All right? Let me do one brief example of this so that you can kind of see what we're talking about. Suppose I take E1, which is a pure sine wave with no phase difference at all. And the second one, I'm going to add to that one which has a phase difference delta of 90 degrees. Let's say the phase difference for the second wave is 9. That means now that where this one is 0, the other one is at a minimum, and it goes up like this, it goes up like this, it goes back down like this, and etc. Right? The sum of these two waves is not 0, all right? But it does have a new amplitude. And the amplitude, if this is E1, and this one is E2, and this one is E2, then there will be a new amplitude, E theta 0. That is the result of adding these two together. And it'll be somewhere between 0 and 2 times E1. But it will get smaller as the phase shift gets larger. Once I know how to calculate this, then, and so in fact, if I actually wrote the sum down, then now I've got a new wave, and I don't know, for example, exactly the phase, but the amplitude turns out, for this particular case, which I have calculated, the amplitude of this one is 2E0 times the, divided by the square root of 2. So in fact, you can see it's not 2 times E0, it's actually been reduced. We're going to calculate what this factor is, but the point is that once I know what this amplitude is, this is E theta, and this amplitude is E theta 0. Okay, that's the amplitude. Okay, now when we meet next time, or you can read the alternative explanation in CATS. I used this explanation from Giancoli because I thought it was a good way to learn it. You calculate how to calculate E theta 0 as a function of this phase difference. And then from that, we're going to calculate how the intensity changes with phase. We ran out of time, so I had to stop.